Hello, I am Murat Görkem Dinçsay. In this project, I am responsible for the hardware design.
Hi, my name is Batuhan Yeşildal and I'm responsible for the embedded system software.
And I am Abdullah Yıldırım. I was responsible for the machine learning algorithms, and our project's name is Design and Implementation of Predictive Maintenance System using Anomaly Detection and Classification. This is our presentation video.
This circuit is a three-phase sensorless BLDC motor driver, built with a half-bridge topology. Each motor phase is driven by a pair of N-channel MOSFETs. Gate resistors are used to control switching speed and reduce noise, while bypass and bootstrap capacitor ensures the stable high-side operation. Phase voltages are reduced with the resistor dividers and sent to the controller for sensorless back EMF detection. Component volumes were chosen for stable switching, low noise and reliable motor operation.
In this project, we developed a bare metal embedded system for brushless DC motor control and real-time data acquisition. The motor speed is controlled using 5 external buttons, where each button corresponds to predefined speed level. The system uses two sensors, a current sensor and an accelerometer. Both sensors operate at the sampling rate of 500 Hz, and the internal filtering features provided by the sensor modules are utilized to improve signal stability and measurement accuracy. Sensor data are acquired continuously and transmitted to an external system using UART with DMA to enabling efficient and non-blocking data transfer. By using interrupt-based control, DMA-driven communication, and a structured main loop, the embedded software achieves reliable real-time motor operation and data acquisition without an operating system.
To ensure data diversity and robustness, the motor is operated under multiple fault conditions such as normal operation, imbalance, broken propeller, impact and overload. Additionally, each condition is recorded at 4 different motor speeds, which introduces natural variations in the signal patterns. The incoming data stream is segmented using a sliding window approach with a window size of 256 samples and a 50% overlap, allowing us to capture both steady state and transient behaviors. For each window, fast Fourier transform is applied to the X, Y, and Z vibration signals, transforming the data into the frequency domain where mechanical faults become more distinguishable. The FFT magnitudes are log-scaled to stabilize the dynamic range. In addition, the mean and standard deviation of the motor current are extracted to capture load-related effects. All extracted features are normalized using a standard scaling approach before classification. Fault classification is performed using a multi-layer perceptron neural network. The model consists of 2 hidden layers with 128 and 64 neurons, relay activation functions, and a dropout rate of 0.2 to reduce overfitting. Training is performed using the Atom optimizer with a learning rate of 0.001, a batch size of 64 and a 70 epochs. During real-time operation, a rule-based idle detection is applied based on a current threshold. If the motor current is below this threshold, the system directly classifies the state as idle without invoking the neural network. To interpret the learned feature space, principal component analysis is applied to project the high-dimensional features into a 2-dimensional latent space. The PCA plot shows that different fault conditions from distinct clusters, despite variations in motor speed. Some overlap between impulsive faults such as impact and broken propeller is expected. However, the overall separation confirms the effectiveness of the FFT-based features. All results are presented through a real-time graphical user interface. The GUI displays time domain vibration signals, motor current measurements, system status information, and a live projection of the operating state onto the PCA latent space. Due to sliding window-based FFT processing, there is an intentional delay of approximately 3 to 4 seconds, as the system must first accumulate enough samples for reliable frequency domain analysis. As a result, the motor's physical condition is reflected in the GUI and the PCA plot a few seconds later, representing a trade-off between temporal resolution and classification reliability. Overall, this system demonstrates an end-to-end predictive maintenance solution that integrates signal processing, machine learning, and real-time visualization.